Hello everyone, my name is Jonathan Vicente from Federal University of Santa Catarina. Today I will present a study called Temperature and Pressure Sensitivity of the Laminar Flame Speed of Diisobutylene air mixtures. So, laminar flame speed is a main physical-chemical characteristic of fuel-oxidant mixtures. The study of this property is focused to obtain reliable data to test and improve chemical kinetic mechanisms, besides to characterize the behavior of the burning characteristics of the fuel, composing a more consistent database. Diisobutylene is an important additive used on the formulation of gasoline surrogates. This fuel is composed by two isomers and is a representative of the branched alkenes present in gasoline. To a better comprehension and improvements on the gasoline surrogate formulation and development of new fuels, it is important to evaluate its combustion characteristics, like laminar flame speed. On this way, this study aims to investigate the influence of temperature, pressure, and equivalence ratio on the laminar flame speed of diisobutylene air mixtures. The measurements of this property were obtained in a constant volume reactor installed at the Combustion and Thermal Systems Engineering Laboratory. The conditions used on the experimental tests were the temperature of 420 and 460 Kelvin, pressure of 1, 1.5 and 2 bar, and equivalence ratios from 0.7 to 1.4. The results were compared with N-heptane and isoctane, the primary reference fuels. In this topic, I will present the concept of experimental result treatment and the calculus of the laminar flame speed. The constant volume reactor is a spherical chamber, and through the treatment of the experimental result, it is possible to obtain the flame radius propagation as a function of time. With the rate propagation of the radius and some assumptions, it is possible to estimate the laminar flame speed using a correlation with the gas density of the burned and unburned mixtures. Due to the stretch and curvature of the flame, it is necessary a correction. The correction can be obtained by the introduction of the stretch rate and using the Markstein length. The laminar flame speed is obtained by fitting the results, obtaining the estimated values for laminar flame speed and Markstein length, and this model presented here is known as the linear model. Kelly and Law proposed a more comprehensive model, and is known as non-linear, which is also based in the fitting of the values to obtain the laminar flame speed and Markstein length. In this work, we use the laminar flame speed obtained through this second model. Now I will present the results of this work. These figures present the laminar flame speed of N-heptane and isoctane at the temperature of 398 Kelvin and pressure of 1 bar. The results were compared with the work of Dierenberg et al. And Monteiro. The study conducted by Monteiro was developed in the same experimental apparatus, and these tests were used to validate the workbench. It is possible to observe that for both fuels, the results are consistent and presenting a good agreement with the literature. Just for the N-heptane, at some equivalence ratios, the results are above of the upper limit by the prediction using the equation proposed by Monteiro. These equations proposed by Monteiro to estimate the laminar flame speed for N-heptane and isoctane is correlated with the equivalence rate and temperature, with no dependence of the pressure. So in this work, we are proposing different pressures, and due to these different conditions, we are also using the experimental results to present our own equations for N-heptane, isoctane, and diisobutylene, including the dependence of the pressure. Now, in respect of the results of the tests proposed in this work, here is presented the results for temperature of 420 and 460 Kelvin, and the pressure of 1 bar. It can be observed that the increase in temperature results in higher values for the laminar flame speed, an average increase of 9 cm per second for all the fuels. High temperatures increase the dissociation reactions that produce free radicals. These radicals initiate the combustion reaction, which is why the flame spread velocity increases. Also, it's observed that the results of diisobutylene are nearer from the results of isoctane than the N-heptane results. Now, is presented the results for the temperature of 410 Kelvin and pressures of 1 and 1.5 bar. It can be observed that increasing the pressure results in lower values of laminar flame speed, a decrease of approximately 5 cm per second in the region near stoichiometry and 2 cm per second at the lower values of equivalence ratio. Now presenting a comparison of the results of the pressure 1 and 2 bar at the temperature of 420 Kelvin. It can be observed that the laminar flame speed decreased more compared with the results of 1.5 bar. In this comparison, it's observed a decrease of approximately 6 cm per second in the region near stoichiometry and rich mixtures and 3 cm per second at lower values of equivalence ratio. Increasing the pressure, there is a recombination reaction that reduces the concentration of the hydrogen atom and thus compete with the initial reaction by producing the free radicals oxygen and hydroxide. This process tends to reduce the overall oxidation rate and inhibit the combustion reaction, and due to this, the flame speed decreases. The equation to estimate the laminar flame speed of diisobutylene air mixture was fitted using the experimental results for a fixed pressure of 1 bar and temperatures of 420 and 460 Kelvin, and for a fixed temperature of 420 and pressures of 1.5 and 2 bar. The equation obtained is presented here, and it is dependent of the equivalence ratio, temperature and pressure of the unburned mixture. Here is presented the results of the estimated and the experimental results in the condition of pressures of 1.5 and 2 bar at temperature of 460 Kelvin, intended to validate the laminar flame speed predicted by the use of the equation. It can be observed a good agreement of the experimental results with the predicted for the pressure of 1.5 bar. At the pressure of 2 bar, the results at the equivalence rate of 0.8 presents a good agreement, but at the equivalence rate of 1.1, the result is coincident to the upper limit of the equation, and in higher equivalence ratio are above of this upper limit of the equation. These tests were developed with no replication due to the availability of the fuel, and to improve the equation coefficients and compare with the experimental results, we expect to develop more tests in the future. Now the conclusion about this work. The preliminary tests demonstrate that the workbench was working properly to develop the tests proposed in this work. The results show that the laminar flame speed increased with the increase in temperature for a fixed pressure, reflecting the temperature influence. In addition, the increase in pressure for a fixed temperature presents the opposite, tending to reduce the laminar flame speed. The influence of these parameters on the laminar flame speed was observed for all fuels, and the equations obtained with dependence of equivalence ratio, temperatures and pressure for the 3 fuels presented a good agreement with the experimental results, and especially for those for the diisobutylene air mixtures. And for the future works, the group hopes to develop further tests to improve the equations by replicating the tests and introducing 1 month more temperature. And here I finish my presentation, and thank you for watching.